Hey everyone, my name is Parker Geary, and I'm going to be doing the leading for we work with Chris, Carter, and Jackson. Next week we're going to be doing the gas turbine jet engine experiment 5. So this is a picture of the equipment that we'll be using from Turbine Technologies. It's their turbogen jet engine gas turbine hybrid setup. And the goal of this experiment is to fundamentally understand how that machine works, how it relates to the Brayton cycle for a jet engine, how that can generate electricity, and understanding some motor efficiencies. This on the left is a picture of the entire enclosure with the included electronic setup, and this is the motor more up close. So if you'll notice, I said electricity, but we're doing a jet engine, so you don't normally think those two things go together. But in this case, the way they have their jet engine set up, it does. So air will go in through the intake, go into a compressor, be compressed, and in between the compressor and this power turbine is a combustion chamber where fuel is mixed with some form of ignition, and the fuel is combusted to generate energy, which then flows through this turbine and out this nozzle. The turbine is spun and connected to a shaft directly connected to the compressor to drive it so that the system continues to compress air and take more as it goes. Now that is a normal jet engine on the left that you see here. This entire back bit, starting at this red cone, is what Turbogen does with this experiment. So they have this big deflection cone positioned right behind the end of the nozzle that deflects the thrust coming off from the air out of the nozzle into a second turbine, which drives a shaft connected to an alternator to generate electricity that can be measured out of this back part. So yeah, that is all based on the principle of the Brayton cycle at the beginning. So if we ignore the second section of the turbine and we just look at what is a Brayton cycle, to review, a Brayton cycle has 4 main positions: adiabatic compression, constant pressure heat addition, adiabatic expansion, and then constant pressure cooling. And you can see the PD and TS diagrams down there on the bottom for an ideal situation of this, because the lines are very straight, which we do not expect in a real experiment, because you'll have to account for compressor efficiencies and turbine efficiencies, which are typically somewhere in the 80% range. So those lines will not be exact. So this section has a back part that is an alternator. How does an alternator work? Basically, it generates AC current by putting DC current into a system. So you have this wire wrapped around this center rotor that's basically floating in between these two stator portions, or 3 stator portions. There's only 2 pictured here, but normally they have 3. And current runs through that wire in the form of DC current, and that causes an electric field to be generated as the current flows around this piece of metal, which then makes this electromagnet spin. And that, as it generates an electric field, will draw it closer to the stators as it moves. And as it moves, those stators will have an induced current from the center rotor getting closer and farther away from them, which then creates this electric field and this alternating current and voltage that you'll see output in this graph. You see A, B, and C for the 3 stators that are normally in your alternator positioned around, and they're out of phase because they're set in usually 120-degree increments, because there's 3 of them. All right, so that's all fine and dandy, but how do we actually calculate anything on this? We have to measure temperature and pressure mainly at a bunch of different points in order to get it. So you'll notice P1, 2, 3, and 4 will follow your main Brayton cycle, being your compressor inlet and exit and your turbine inlet and exit, which we measured with some kind of temperature probe and pitot-static pressure tube, as you see on the left. This is the one from the inlet of the compressor, which is just the easiest one to see. The rest of them are inside the engine. Additionally, there are ways to measure the engine RPM and the generator RPM at the back, as well as the fuel flow. And then what we're trying to get is this current and voltage coming out of the back. And we'll calculate the pressure and temperature out of the back of the power turbine that is behind the deflection plate as well. So, how are we actually going to do all that? The most important thing, this lab can be slightly dangerous, being that it is a jet engine, so it's a controlled explosion. So most importantly is your PPE. Your safety goggles as well as your earmuffs will be required because it gets loud. Additionally, fire extinguisher on standby in case something happens. Hopefully nothing happens, but just in case. This is on a cart system, so make sure the wheels are locked, or it can just move across the room because it is a jet engine and it is converting it into electricity, but it still outputs some amount of thrust out the back. So we wouldn't want a jet engine flying across the room and hitting people. That would be kind of bad. And initially, so to begin the experiment, you have to make sure everything is off and everything is clean. All of the intakes, points in the system where debris could get in, make sure there's not. Very important. Additionally, you'll verify the oil and the air pressure levels before starting the experiment, just to make sure everything is good, everything is constant, and then hook up the computer to it so that it's ready to start measuring once it comes. So then for actually starting the experiment, you'll turn on the master switch, which is that one all the way on the left. And you'll see these different panel meters along the front here. The important thing are these levers on the side, which need to be set all the way to the minimum to begin. And the load lever has a pin, and so you put the pin in it to make sure it doesn't just move like crazy. Then you will, after making sure everything is initially set to 0, throttle the thing all the way to the maximum, just instantly, to make sure that it works. And it should light up a little flag that says, hey, you just put this at the max. And then you say, okay, it works, and you put it all the way back down. And then you're ready to go once you know that your warning flag works, because you're not going to do that during the experiment. You just have to make sure. So then you'll hit that green button right there, noting that that red button stops it at any time. So if anything does go wrong because you didn't do something right, hit the red button. And it will take a long time to restart, because you have to go through all these checks and make sure the system is reset. But it's better safe than taking an extra hour. So during the procedure, what's going to happen, this is a software that's connected on the computer, so you will adjust that power lever that I was talking about. That controls how much fuel is flowing in through your engine, so it will control directly how much electricity is being output by how fast the motor is spinning, how much fuel you're combusting. So you'll collect the data off of this software, log into a file. This software plots some of the data things for you that you need, and the rest of them will be gathered through the Excel file later to compare different plots, and then you'll take a picture of what's happening so that you know for later reference. These are some of the important equations, some of the things we have to calculate. We're trying to find work basically throughout the entire system as well as energy. So you're going to use the change in enthalpy throughout all of these. You'll get that from steam tables based on the pressure and temperature that you found experimentally. And then for the power turbine in the back that's generating the electricity, you'll do the same thing with the change in enthalpy in front and behind the turbine. And then the efficiency of that power turbine is going to be your RPMs generated, because you're not looking for thermal efficiency, you're just looking for how well the system works, how well it generates electricity. So you're basing it on motor speed versus generator speed. These are some more equations that we will be calculating for the compressor at the inlet. We'll need all the different flow speeds so that we can understand what's actually going through our engine. So we'll need velocity, volumetric flow, mass flow, and Mach number, which are all derived off of each other, starting with the Bernoulli principle up there. So you can see the equations and some sample numbers, assuming standard temperature and pressure conditions at sea level for our thing. So before we finish, really don't forget these things. It's hot. There's a case on it for a reason. Don't open it. When the thing is running, it is an engine and it is exploding fuel, so don't touch it. Also, wear your earmuffs because it's loud. And everyone else will be in there and it'll be loud, and that's okay, but just wear your things, protect yourself. And that power lever that I talked about, I said at the beginning, you'll put it to the max. Don't actually do that during the experiment. Very important, because if your engine is running and you immediately throttle as much fuel as possible and something goes wrong and all of it explodes at once, you could destroy the engine. And that thing is really expensive and we don't want to do that. Also, no debris. Make sure you actually check everything thoroughly first before you close it and start the whole system, because if there is debris in there, we are exploding things, as I've already said a couple times. So debris in there blows it up, bad time. Don't do that. These are my references. Any questions?